Okay, welcome back. So this is our new recitation, which will be about power series and in particular Taylor and Maclaurin series. And if you remember, last time we discussed absolute and conditional convergence, and today, as I said, we will discuss power series and particular power series representations, basically. Okay, let's see. Let's start with this, with the first problem. Okay, so we are going to try to find some of the following series actually. So let me start with the first one. For instance, start here, part A. Okay. So for part A, actually, we will use very important idea. Okay, so the idea is, so let me write it down. So the main idea is the following. So the first step, actually, somehow we try to generate new series from a known series, actually, by using, for instance, term-by-term differentiations or integrations or some algebraic manipulations, okay? We start with some, if you like, test series. We start with some very well-known series, and we try to manipulate this series to obtain the new one, okay? So idea, generate new series from known ones, okay? From the known ones, okay? As I said, how? So basically using, for instance, term by term differentiation or integration or maybe certain algebraic manipulations. Okay, etc. So this will be our main idea. And the second step, once you do this, actually, another idea is we try to express certain complicated functions by using just simple polynomials. So we try to, so in terms of polynomials. But infinite polynomials, actually. This is the reason why we use those series, basically. So let's see. This will be our main idea. Let's go back in the first part, for instance, here. Let's try to generate this series, okay, by using some known series. So we should recall, of course, some of the basic representations, actually. For instance, we should record the following. So this is the very basic one. Actually, this function can be expressed by using this series, okay? But be careful. This is actually, there is a missing information here. So this equality here is true, not for all x, but with some restrictions, okay? We should always specify this kind of restrictions over here. So this is not true, the here, so this is not true unless x is less than 1, absolute value. Therefore, we always, once you define such an equality, you always specify the interval of convergence, okay? So this is actually the interval of convergence. Okay, this is not true always. This is true if you are in the interval of convergence. Fine, so these are basic ideas. So let's start with this series and try to manipulate. So actually, just start with the following. So start with this series. So let me give you the recipe. So start with this series, actually, that one, which is very well known. Okay, oops, okay, 0, So what is it? X to the n. Start with this. Now the first manipulation is just to take derivative, take the derivative of both sides. Okay. So in the right-hand side, of course, we have, so the right-hand side, we have term by term differentiation. Be careful. So this can be done by Taylor's theorem. So you should go back and check the lecture notes why we can do such a move, basically. So if you do this, so actually we have something like this, right? So once you differentiate, this is the left-hand side. So what about the other parts? When you differentiate, we have something like this, and nothing change for this interval of convergence. But be careful, because of this here, actually our indices now starts from 1, basically. Otherwise, it won't be a polynomial, right? So we have a shift for indices, actually. Okay, this is the first maneuver, basically. Now let's do this one more time. One more differentiation. Okay, let's see what we have. If you differentiate, of course you have okay, 2 and minus 2 divided by 1 minus x cube, right? Is that correct? I guess so. And similar here. So now we have n times n minus 1 times x to the power n minus 2. Still, we have similar kind of domain of convergence, so no problem. But as I said before, be careful now indices, so we have a shift. But we almost done. So if you look at carefully, this right-hand side, series on the right-hand side is almost what we are looking for. Let's go back and check here, right? So this one, we always almost obtain this kind of series, but one more move actually we need. So let's see. We almost done, but somehow we need to get rid of this minus 2 over here. How to get rid of this? Just multiply each side by x squared. Okay, so if you do this on the left-hand side, okay, x squared, sorry. So 1 minus x, right, cube. And when you multiply, so everything by x, so n times n minus 1 times x to the n. Okay, with this same domain of convergence. Okay. Fine. Actually, we are done. And so what about part B? So this is exactly what we are looking for. So let's see, part B. So let's see, let's try to, let me write it down, part B. So we have a series like this, so let us write down. Okay. So here, part B. So for part B, we just observe, okay, observe the following. So, so what we have something like this. So this is given, basically, right? So this is given. So a kind of a manipulation, actually, if you look at carefully, we have a kind of a manipulation like this, algebraic manipulation, which is something like this. So I just change where the indices start, but of course for the equality we need exactly the oops, oh, okay, I did nothing, so sorry, oops. So that is a trivial move, no problem. But in the second part, now let me change the indices where it starts basically, right? And therefore we have minus a2. And a2, if you compute, so let me denote this part, okay, this part an. So a2 is, okay, 1 over 4, right? This is a2. Is that correct? No, right? So it's not a2. Oops, okay, a2 is, oops, sorry, 1/2, right? Fine. Let's see what we have. So why we are doing this now? If you look at carefully, maybe one more step, n starts from 2, n times n minus 1 times, actually we have 1/2 to the power n minus 1 over 2, right? And if you go back and look at part A, we have actually, so by part A with x equals 1/2, right? So if you go back and look at what we already find in part, so where is it here? Here, that part. So let's see what we already found here. This is, we have exactly the same expression on the right-hand side, right? But exactly when x equals 1/2. And therefore just apply 1/2, and let's see what we get. When you apply 1/2, so just substitute x equals 1 over 2, you have minus 1 over 2 here, minus 1 over 2 divided by 1 minus 1/2 and cubed minus 1/2. Okay, therefore actually we are done. We compute this series, okay, by using part A, okay, with the specific value of x. Okay, you can compute the rest, it's not that much important. And so what about part C? Okay, part C. And so let's go back and check what was part C. And we really want to understand somehow this expression here. So where is it? This expression, right? So this is our series. So let's see. Since of course, as before, we use our main approach. Remember, we just start with some very well-known series and manipulate it, right? So let me just as a recall, maybe let me recall. So the recall is the following. So this series actually n starting from 0, x to the n factorial. This is actually e to the x, right? Power series representation for e to the x. And the best thing is this is true for all x, okay? Remember, the previous representation in part A was only true for specific values of x, not for all x. Okay, in our case, we just define our sequence to be, okay, something like this. And therefore, just let me write it down in this way, if you like. So nothing changed, something like this. And then let's see what we have. Then just observe that. So we start with, we wish to understand this series, right? This was part C, the question in part C. But if you look at carefully, so we can manipulate it. We almost have exactly the same series in the recall, here in the recall. but not yet. But a small maneuver actually gives us what we want. Right? If you write it down, something like this, now we are done. Actually, now we can use what we have in the recall, right? So this is exactly, so by recall, but with a specific values of x, with x 1/2, this is exactly, I mean, this part is exactly e to the 1/2 and minus whatever a1 is, and a1 is 1/2, I guess. Okay, and so therefore, so we are done. Actually, the series we are looking for, we just computed its value, and factorial is just e to the 1/2 minus 1/2, and that's okay. Basically, this is how we use certain very well-known series to deduce, I don't know, some meaningful information for the series we are looking for. Okay, we somehow try to start with very well-known to generate what we want. Okay, basically. Okay, for instance, in the next problem, we are going to, I mean, we try to find Maclaurin series for the given functions. The idea is always the same. Why we are doing this? Because, for instance, evaluating those functions may be sometimes hard, but if you express them in a very simple way, for instance, in terms of polynomials, then uh, computations maybe turns out to be rather easier. For instance, next time we will see certain applications for this idea. Okay, part A. Let's try to understand part A. So we try to find Maclaurin series for ln x plus 1. So let's see. The similar idea start with very well-known prototype series. For instance, start with this one. We already know that this function can be represented by this series, okay, x to the n, but not for all x, with some restriction here. So we start with this one and try to manipulate. So we modify it as follows. So start with this and modify it. So how to modify is as follows. So the first modification is just replace x with minus x. It's a very naive modification, but it helps us almost what we need. I mean, to find what we need. So if you do this, so we have something like this, right? Clearly, x to the n, and nothing change here with this restriction. And fine. And now we almost done. And if you integrate this, integrate with respect to x, integrate, of course, both sides with respect to x. So what you have, of course, you have ln 1 plus x, right? Logarithm. And right-hand side, we have term-by-term integration. And of course, we have something like this, an expression like this. Okay, with this same domain of convergence. But we should be careful. So this domain of convergence may not be enough. I mean, we should be careful over here. Okay, we should be careful. And actually, the integrated series converges everywhere on the interval of convergence of the original series, so no problem. But it may possibly become convergent at one or both endpoints. Okay, so maybe a remark here. The remark here, the resulting series after integration. So the resulting series, so after integration may, may possibly converge, at one or both endpoints. Okay. Therefore, we should check endpoints separately. So for sure, it is convergent, exactly the same. At the exactly, on the exactly the same domain, but we may have extra convergence behavior at the endpoints. Therefore, we should check the endpoints for the resulting series after integration. We should check the endpoints. Therefore, as a third step, we should check the endpoints. Okay, so let's check. Let's check what is one of the endpoints is. So for x equals -1, for instance. For x equals -1, actually nothing to check because actually left-hand side is undefined. So left-hand side undefined. Okay, so it doesn't much make sense to check x equals -1 if you check the limit. ln 1 plus x as x approaches the -1, right? Turns out to be infinity. Fine, so it does not exist. So left-hand point is not included. So this is our conclusion. So what about the right-hand point? Just look at, if you substitute x equals 1, what we have on the right-hand side, -1 to the n when x is 1. Okay, we have 1 and divided by n plus 1, right? Only term we have on the right-hand side. But this is converge, right? This is converges by alternating series tests, right? Remember, so if you let this thing to be Bn, let's say, observe that Bn times Bn plus 1 is okay, negative, and if you look at Bn absolute value, it decreases to 0, and so use alternating series tests. Okay, therefore this is convergent. Therefore we should include the right-hand point. Okay, for the resulting for the resulting series. Okay, so for the interval of convergence for the resulting series. Okay, so therefore the interval of convergence for the resulting series will be what? -1 is not included, but 1 is included. Okay, so we should be careful. Fine, so what was part B? So let's see, let's try to understand part B. So which is this one, right? So part B. Okay, part B. So for part B, we should recall that e to the t, actually, we discussed this before. This is exactly, okay, n from starting from 0, okay, n factorial. This is true for all t. Okay, we have this recall in the first place, and let's try to manipulate it, right? So just notice that actually, what is the first term? First term is 1, right? And the next part, t to the n divided by n factorial. So So with this observation, e to the t minus 1 is just n starting from 1 and t to the n divided by n factorial. Okay, and so, and clearly we already have this. Okay, divided by t, right? So this is t, oops, n starting from 1, t n minus 1 divided by n factorial for all t, right? Except 0. So because the left-hand side doesn't much make sense to have 0 here. But undefined. Now we integrate both sides. So integrate both sides with respect to t. With respect to t gives the following, basically the following observation, right? So the following expression, if you like. So from 0 to x e to the t minus 1 divided by t, this function, and dt, right? And just integrate term by term as before. There is a theory behind this, so you should go back and check the lectures actually for more details. And actually we have this, right? So term by term integration, if you like. Then fine. So let's do this. And what is it? X to the n divided by n times n factorial. Okay. Okay, and then for all t. Okay, fine. Not 0. So that's all. So let's see. Let's look at the other parts. So what was it? So part C, x divided by 3 minus x squared. Okay, let's see, part C. And so part C, actually, we will use more or less the same idea. Let me start with the following series. As you see, we always use more or less the same approach, right? So we start with very well-known one, for instance, this. As before, be careful. Oops. Okay, something like this. So we start with this and modify it. As before, just replace. Somehow we want some kind of x squared term, right, in our series. So we wish to generate, we wish to see something like this. Just replace x with a term like this, x squared divided by 3. If you do this replacement, so let's see what we have. Right, we have this, of course, no problem. And n start from 0, x to the 2n divided by 3 to the n. But now you should be careful, because if you do this restriction, we have something like this, right? Be careful. I mean, how to do this? It's not that much hard, because if you replace x with this number, this was what we have, and this is exactly, okay, we don't need absolute value. Okay, a squared less than 3, and this tells us basically absolute value x is less than square root 3. Okay, fine. So what else we need? And we also want some kind of x in the numerator, right? So multiply each side by x. So if you do this, actually we have 3x. So let me rewrite everything in a more familiar way. So just equate the denominators, blah, blah. So we have this, and starting from 0 and multiply x gives us 2 to the n plus 1 divided by 3 to the n with this domain of convergence. And we almost done. We don't need this 3 here, actually. So the finally, and so x divided by 3 minus x squared. This is what we want, basically. We want to generate. So this is just 2n plus 1 divided by 3 to the power n plus 1, and with this interval of convergence. Okay, so we did this. We really find this. Remember part C, this representation for the series. Okay, this one, and we are done. And what about part D? So let us do part D, and as before, start with very well-known series, which is this e to the x. Because why? I mean, because the series we are looking for basically involves some exponential. Therefore, it's logical to start with a series representation for the exponential. Okay, this is the logic basically for all x. Fine. Let's try to manipulate this thing, this expression. So let's see. First manipulation, we need a term like this. Then on the left-hand side, we have this, and just manipulate right-hand side. So for the right-hand side, of course, we have this term, and divided by n factorial, and we have x to the n, I guess, right? And still for all x. And the second step, so what we need, and the second step, we just observe that, just observe e to the, I mean this, so let me write it down. Actually, if you start with, I mean, just write down the first term, a0, which is just 1, right? This is a0, actually, when n equals 0. Okay. This is a, what is this? Sorry. Okay, so what was it? I'm sorry. So we have this and this kind of series, right? Okay, this is exactly the when n equals 0 plus n starting from 0. So what's going on? Okay, sorry. Okay, minus 1 to the n, 2 to the n, and divided by n factorial and x to the n. Okay, and therefore, what does it tell us? Actually, 1 minus e to the minus 2x is exactly this term, right? So minus n starting from 1, minus 1 to the n, 2 to the n, divided by n factorial times x to the n. And if you want, so this term is exactly, just get rid of this minus, right? This is exactly minus 1 to the n plus 1 times 2 to the n, and divided by n factorial times x to the n. Okay, and the third step, actually multiply each side by 1 over x. And therefore, we should be careful. This can be possible for all x, not 0. And therefore, 1 minus e to the minus 2x divided by x is, okay, summation n to the, okay, 1 minus 1 to the n plus 1, 2 to the n, okay, n factorial, x to the n minus 1. Okay, as before for all x. Okay, maybe we should mention not 0. Okay. So we have the series expression, or Maclaurin series expression for this thing. Okay. So in the next problem, we will basically discuss Taylor series representations, but maybe before this we should take a break. Okay. So let's